It's a great pleasure to introduce you to Rafick Sekaly. So he's a researcher at the Case Western University in Cleveland, USA. And he's one of the world leaders in HIV research. And to me, he's also one of the world leaders in systems biology. So I follow his work since 2009 or 8, when the first systems vaccinology paper came out. So I hope you realize that he works with several different fields, not only HIV research. And he got a major grant of $11 million to study the IL-10 blockage. Are you going to talk about this, Rafick? No, right? Are you going to talk about the IL-10?
No.
Okay, so
it was last year.
It's going to be a new stuff. So with that, Rafick.
Okay. Well, that's right. I'm sorry I didn't go to the beach yesterday, but I at least give me time to make my talk. So, okay. So thanks a lot again for inviting me, and it's always a great pleasure that I'm here. And so I'm going to talk today about, as Michael Lederman knows very well, projects in my lab take a lot of years to finish, but at the end of the day, they do finish, and they hopefully make a difference. A lot of people in my lab work on the HIV cure. Some work on vaccines. A growing number of people now work on cancer, and maybe next year I'll present to you a lot of the work we do on cancer. And I think the idea, and I think one of the major reasons why I moved from Canada to the US is really because I want to do science that was going to make a difference, and the best way to make a difference is to work on human interventions and look at the immune system as it responds to interventions, and there's a really good idea of what works, what doesn't work, and why it doesn't work, or why it works. So one of the major projects in my lab since 2005 has been the work that we've been doing on HIV cure, initially with Nicolas Chaumont when he was in my lab, and then on our own as we moved from Florida to Case Western. And again, the idea was not to find a cure, but to bring a contribution to the immense work that a lot of us are doing on the HIV cure. And I think a cure became, I think, possible when we got, the two patients, the Berlin patient and now the London patient, that showed, that upon autologous bone marrow transplantation, you're able to, not autologous, but allogeneic bone marrow transplantation of CCR5 modified T cells, you were able now to, or CCR5 or delta 32 cells from subjects who were homozygous delta 32 mutations, you're able to sustain, in the case of Berlin patient, now almost, 10 years of undetectable viral load. And in the case of London patient, about now almost 2 years of undetectable viral load. So we still don't know how this works, but how those patients were eventually completely cured, because there's a lot of other interventions that were tried in almost a similar way, which unfortunately not get yet to the same quality of data. There was the Mississippi baby, there was several studies from the Boston patients, the San Francisco patient, and then there were interventions done by the MHRP in Thailand, where people were treated very, very early in infection, with the idea that maybe that would allow them to limit the reservoir and allow the immune system to control the reservoir once it's unleashed. Unfortunately, none of these have yet led to the same outcome as the Berlin patient. So, meaning, that, it's going to be not an easy task, to get there, and meaning that you have to confront a lot of people, a lot of problems, a lot of challenges to be able to eventually become and eradicate HIV. The first one is of course, finding a virus, first at the level of cells and the level of tissues, and there's been a lot of work, again, from our group, but also from many other groups, trying to identify specifically the cells where the virus hides. And because we don't have yet really standardized good assays to be able to measure what you call the replication-competent virus, we're still at odds, in trying to define which subset is the one that has, the most replication-competent virus. And I think, that I think the new assays that Bob Siliciano has been able to develop, the work that now allows us to look at viruses at the single cell level from Mary Kearney and other groups probably will shed some light there. But then, of course, I mean, one major challenge that we all have is that we're dealing with people that have been treated with antivirals for 10 years. And some of us have the dream, that these people have an intact immune function. And unfortunately, this is not the case. Because although, I mean, we are able to restore exhausted HIV-specific T cells with anti-PD-1, but there's very limited studies now with anti-PD-1 in HIV-infected subjects. For many reasons that you might be able to understand. So being able to restore exhausted HIV-specific T cells is still a problem. But the real problem is, which a lot of us do not address, is the innate immunity. And innate immunity, if you're ever going to be able to prime a T cell, you need an innate immune cell to be able to prime the T cell. And in HIV infection, especially in Untitled Chapters, where you have reservoir viruses, which are mostly escape mutations, I mean, you need to be able to prime T cells to those escape mutants. And that's something that we are not carefully taking care of. I think the work that Gilead is doing with their TLR7 agonist might allow us, I mean, to get there. But I think there must be much more important effort, I mean, to target this. And of course, I mean, the last point, which is going to be a little bit the story of my talk, is that in case you unleash, I mean, the virus by stopping treatment, you need to be able to protect, I mean, your CD4 T cells from getting infected. So you need to be able to engineer CD4 T cells that can be resistant to HIV infection. So if you really want to, aside from doing bone marrow transplantation, which are a very risky business, and you want to get to an HIV cure, I think, I mean, you need to be able to develop long-lived host responses that will eventually be able to control HIV, and that's something that we need to learn how to be able to engineer such responses. So if now you look at the landscape of therapeutic approaches to get to a cure, of course, you can gene-modify stem cells, which you have the lean patient, the non patient, and I'm lucky to be part of a trial with Seed of Hope and John Zaya, and Sangamo, where we soon be looking at 12 subjects that received autologous bone marrow transplantation with bone stem cells that have been depleted of CCR5. We are also, together with Antigen, generating a new generation of CAR T cells, which are HIV specific, and the work of Boris Dropulic and his colleagues. We have now a second generation CAR T cells of HIV specific, and soon we'll be submitting to the FDA a clinical protocol that's almost complete. So hopefully within next year we'll have HIV specific CAR T cells. I think you'll hear a lot from Rick about the broadly neutralizing antibody and some of the, I don't know, Rick, if you touch upon the vaccinal effect that Michel Nussenzweig has described. And of course, there are therapeutic vaccines, and I think those therapeutic vaccines, I think, will only work if we are able to restore T cell priming. There is some proof of concept that this therapy works from the group of Novio and HPV vaccination, which is very highly scalable. But I mean that still needs to be improved. So and to be applied to HIV. So in my lab, what we do, we try to understand what's going to make a good immune response from what's not going to be a good immune response, and so what we measure lots of different parameters with the idea that not a single parameter is going to be able to give us an answer. So when you want to generate an immune response, you need to have a signal that's going to trigger a molecule that's going to trigger a signal. Those molecules can be prevalent in the extracellular space. They can be cytokines, they can be metabolites of host or bacterial origin. So we measure comprehensively using either metabolomics or high-density cytokine analysis. We measure everything that's in the plasma. Then what we do is the tools that Bob so elegantly described, and we use flow cytometry to be able to dissect the cells in which now are getting signals. And then we move on now to the transcriptome, where now we look at the whole the complexity of the pathways and gene processes that are being induced, with the idea that if you see a gene that's being upregulated or a pathway that's going to be upregulated, because yes, I mean there is a transcription machinery and transcription factors that are present there, which are going to be able to trigger that pathway. But if that pathway is not being triggered, it doesn't mean, I mean, the machinery is not there. It could mean a completely different thing, and that's something that, again, with time we are learning, which is, I mean, the fact, I mean, that epigenetics and chromatin, the state of chromatin, can completely prevent, I mean, the machinery from being operational. So if you took a gene array and you are able to see that a gene is being upregulated, that's great. If it's downregulated or it's not being expressed, it means that probably chromatin is a lock conformation. And I think for those of you who have read, I mean, recently, a lot of work on trained immunity and how innate immune responses can be completely modified by epigenetics and signals from the outside of metabolites. I mean, that really tells you that you also need to look very closely at epigenetic regulation of transcription. And that's something that we all do. And at the end, I mean, once we have, I mean, the signal that's going to elicit that's going to trigger a cell, we define the cell, we define the machinery, we define whether or not it's due to epigenetic modification or autoactive transcription. Then now I call my bioinformaticians, I give them all the data, and now they're able to generate models and predictors of whether someone is going to be able to respond to a therapy or not, and they give me a mechanism by which now I can decide whether, I mean, why you're going to respond and why you're not able to respond. So if you're interested to do this work, I mean, we can take, as I said, a lot of time. You can call me and we'll discuss. So, and if you have especially a very interesting clinical trial with very well-defined outcomes, I mean, I think, I mean, that where, of course, everything starts is to have a well-powered clinical trial in which, I mean, you are able to have very well-defined. So I don't know where, no, this is not working. Okay, so I'm going to give you one example that we've been doing in my lab, which is a work that we've been doing for the past 8 years, since I was still in Florida, on two trials that were done by Sangamo, and where we looked at the impact of CCR5 gene-edited cells on the decay of the HIV reservoir and control of HIV replication. So one day I was in Florida, not at the beach, and Steve Dix calls me and says, well, you know, this company called Sangamo, they want to talk to you. You know, they've been infusing CD4 modified T cells, and they've been finding out, you know, that those cells, you know, trigger an increase in CD4 T cells for about almost 2 years, where you go from below 350 to about 500. So, and the idea was maybe, yes, we're rewiring some output and generating de novo T cells. So I said, well, okay, send the samples, and we'll try to find out what's going on there. So for those of you who don't know what Sangamo does for their life, and is that they use a different technology. I mean, this is really the ancestral technology of gene modification. Since then, you have talons, and now we have CRISPR. But they were using zinc finger nucleases. Those zinc finger nucleases, what they do is that they cleave the DNA, generate double-stranded DNA breaks, and those double-stranded DNA breaks get filled by nucleotides in a very random way, and that allows, I mean, now the gene to be completely disrupted. So they target the zinc finger nuclease to the gene they want to inhibit, and then that cleaves the DNA, and now you generate a mutated transcript that is not functional anymore. One point I would like you to remember is that when you cleave the DNA here, it's filled by nucleotides, and in fact, every cell in which now you cleave the DNA is going to be filled by random nucleotides. So at the end of the day, you have gene expression, gene signatures, which are specific for each T cell that has been mutated, and now we can use that to track the cells all along the treatment. So they did 2 trials. The first one was what we call the 902 trial. This trial enrolled 9 HIV positive subjects on long-term ART. A mix with CD4 T cell count between 200 and 500. So typical of what we call immune failures or immune non-responders. And in the second one, I mean, they were a little bit more ambitious. And what they decided is to do an ART interruption after infusion. So they infuse the cells. They waited for 6 months before they eventually interrupt the treatment. And in fact, one modification they did in this treatment is that they treated those subjects with cytoxan. What cytoxan does is it depletes completely the CD4 T cell compartment, which gives a bigger niche for CD4 T cells once you infuse them to expand and replace them in the current compartment with cells that have been now gene modified. And based on viral load and CD4 counts, they either extended the ATI, which was 22 weeks after infusion of the cells, or not. And essentially what I'm going to show you is that we identified what we call a T cell stem cell. And if I have time, I'll be able to go through all the biology of the cell and highlight, the impact of the stem cell on CD4 reconstitution, on HIV reservoir decay, and on control of viral load. So a lot of you have seen, the work that Merck and other groups have done on the HIV reservoir, where they've used HDAC inhibitors to decrease the reservoir using, again, a complete variety of technologies. And eventually, none of these trials has led to any significant impact on the reservoir size. Whether or not you use any technique, that you want to use integrated DNA, total DNA, tilde, replication competent. Well, if you look at here, you'll see something which is quite unique, and I think which hopefully will draw your attention. So this is a reservoir as measured by total DNA on those people that have been treated for ART for up to 3 years before they receive the treatment. So you can see they're about in the thousands. And now if you look at 1 year later, you see that the reservoir has decreased. It's almost reaching significance, but only by half a log, if not a log. And now if you go up to 3 years, or 2 years and 3 years, we have follow-up up to 5 years now. That reservoir can go down by almost 3 logs. So there's a continuous decay of the reservoir, which means, it's not like it's not like the shock and kill approach. No, there's something that goes on that takes time to happen, and that's something that's very important in terms of conceptualizing how this become operational. So potentially suggesting that there is, with time, there's replacement of infected cells by cells that have the mutation and now are protected from infection. So that's in the 902 trial where you did not interrupt treatment. Now you look at the 1101 trial where we did interrupt treatment. You can see, in fact, that there's a lot of subjects where we had to put back on ATI after 22 weeks of treatment. But there's a lot of subjects, in fact, 6 of them were not put back on treatment, and some of them for up to, and I'll show you one example, up to 5 years is still not on treatment and has undetectable or below 100 copies of RNA in his plasma of viral load. So whether you look at the impact of the latent reservoir, or if we look at the capacity of this intervention to lead to effective control of viral load, we do see in both instances a positive effect. So then, of course, now we have very distinct phenotypes, and that's where now we start to use approaches to try to decipher what's different between the subjects who were able to develop a control of viremia or a decay in the reservoir, and what's different from those subjects that they were not able to control. So again, one of the things that we do, I think, quite well in the lab is to look at memory. And we've been able, to work a lot on all the features that define all these different deep memory subsets at the molecular level. And we know, that there is those cells move on from a naive cell all the way to a terminally differential effector cells. And in the beginning, those cells have a very good capacity to proliferate. They can have very good capacity to migrate to lymph node. And they're endowed with some stemness, although the way that we were defining stemness at the time was a little bit metaphysical. And I think now we are becoming much more granular and much more educated about the way we define stemness. And with time, in fact, with differentiation, you see, in fact, that those cells, lose the capacity to become stem-like. They lose the capacity to proliferate, but they do what a T cell should be able to do, which is to kill and to become cytotoxic and to get free or to exert effector function that can prime both the innate and the adaptive immune system to exert the function. So we of course have these high multivariate flow cytometry panels that allow us to look at multiple subsets. And if you look at baseline, by looking at now a series of panels, which includes here CD4RA and RO, and now look at CCR7, CD27, look at CD28 and Alzheimer's receptor, you're able now to identify a phenotype of these cells which are in the middle, which have a very low frequency of CD95. If now you go back to 6 months later, 6 months of the infusion, you see in fact that using now the same grading strategy, grading again on those RAR positive cells, now you have a very high frequency of those CD95 high cells. And in fact, when you look at the longitudinally over time, at which cells are the ones that undergo the biggest differences from baseline, it is indeed that RARO CD95 positive cell that undergoes the most sustainable differences between year 3, year 4, and baseline. So that subset which is at the time was novel, and that subset is the one that appears, to be controlling the rate or contributing to changes that we see that potentially correlate with the outcome. So, of course, the second thing that we did was also to look at, we did comprehensive gene array on the cells that, and compared people who responded well to people who did not respond well. And I'm showing you very simple diagrams where I want to highlight to you, in fact, that the subject who responded well had high expression of CCR7. So again, a marker of very, quote-unquote, undifferentiated memory CD4 T cells. They had expression of some interferon receptors or interferon-regulated genes. And if you look at those subjects that did not respond, they do express now markers of apoptosis, markers of inflammation, whether it's the inflammasome or whether it's the interferon pathway. So the way that it seems, that the treatment works is that by highlighting, the stemness of the cells and their capacity not to die and to be able to persist. And now when you correlate, the different pathways that you identify with both HIV, total DNA at month 36, and also the delta in CD4 counts at month 36, you can see that one of the pathways is the one that is associated to the highly differentiated T cells, which is the Mtor pathway. That pathway is completely downregulated in those subjects that have low viral load and low delta CD4 counts, meaning that the downregulation of the Mtor pathway, which is a pathway that leads to differentiation, and that of course is against stemness, is a pathway that you need to control. So then we went on and looked at started to integrate a lot of different other parameters, and I want you to look at this three-dimensional graph and focus first on the size of the dots the bigger the size of the dots, I mean, it's proportional to HIV DNA at day 20 to baseline. So the greater decay is symbolized by larger dot size. So those subjects that have those large dots are subjects that have that underwent, I mean, the largest decay in HIV DNA between baseline and day 20. And what you figure out, in fact, if you look at now what you have here on this x-axis, or here on this axis or this one, you can see, in fact, this axis is the number of TSCM at year 3 and year 4, and this is the number of modified T cells at year 3 and year 4. So if you go this way or if you go this way, it means that you have a lot of modified CD4 T cells that have been gene edited, and they are the ones that have, in fact, the larger dot size, again confirming that increased number of modified CD4 T cells that are the TSCM subset are the ones that undergo the largest decay in the HIV reservoir. So that was in the 902 trial, and if now you look at the 1101 trial, where we not look at reservoir decay, but you look at control viremia, you can see, in fact, I mean, that there was a significant correlation between the frequency of CCR5 gene-edited CD4 RARO and control viremia post-ATI. So here you have increasing RARO intermediate TSCM count, 6 weeks post-infusion, and here we have log delta viral load. So you can see, in fact, that again there's an inverse correlation between the frequency of TSCM and the delta viral load. Again, confirming, and this is what I've shown you here is we looked at over 200 parameters, and these are parameters which are the ones that correlate with the decay in reservoir or the decay or to be able to control viremia. So then we went on and wanted to confirm this. And if, of course, if the assumption is that those TSCM are stem cells, I mean, they're going to do two things. They're going to persist, and they're going to self-renew over time, and they're going to also replace the other cells of the CD4 compartment by cells that are being gene modified. And you remember I told you in the first slide, when you modify the cells, you introduce a mutation in those cells, and you can track those mutations across time in all the other subsets. So we sequenced all mutations in all the different cell subsets, and we took the ones which were the most frequent in that RARO TSCM compartment, and now we look at their capacity to be prevalent at year 3, year 4, in that subset, of course, and all the other subsets. So if they are still present in year 3, year 4 in that same subset, it means that that subset has undergone self-renewal, and that subset is able to maintain and persist. So that's already one conclusion, is that that subset is able to maintain at the single cell level its persistence by mechanism which we are unraveling. And the other component of stemness is that those cells can now differentiate in all the other subsets of the adaptive CD4 compartment, and that's exactly what you see. At year 3, year 4, you're able now to see, in fact, mutations that were unique to that compartment at day 0, and now those mutations are distributed in all the other subsets. Again, meaning that those cells are truly multipotent, like a stem cell should be, and are able now to differentiate into all the other subsets. And in fact, we looked at the same thing in the other trial at week 6 or in week 22, and again we see that mutations that were prevalent at the onset of the infusion, again at week 22, are still present in the stem cell in the 1101 trial and are seeding, I mean, the other cell subset of this compartment. So, I mean, those cells truly seem to behave like a stem cell, at least at the phenotypic and the gene tracking level. And now we can assess, you know, the contribution of those mutations to the reservoir decay. So one of the hypotheses that we were trying to test is whether, I mean, the progeny of those stem cells are being protected from infection, and whether that protection is able now to contribute to the decay in the reservoir or to control viremia. So what you looked here is that the integrated HIV DNA copy and compared responders and non-responders and you can look at baseline. There's very little difference. At week 26, just immediately after the infusion, there's still very little difference. But now if you compare, at week 22, week 14 and week 22, you see that now the subjects that are protected or that are able to control viremia have a very different frequency of integrated HIV DNA in their effector memory cells as compared to the cells, the subjects that were not protected. Meaning that protecting effector memory cells, which are the most thermally differentiated cells from infection, is associated to be able to the control of viremia. And again, if we now correlate the frequency of CCR5 modified cells in TEM, that again frequency is inversely correlated to the delta var load, meaning that the more EM you have that have the mutation, the greater decrease in your delta var load you're going to incur. So the other way, so again, protection from infection of effector memory cells seems to be a major component of the way that those cells are getting, that those subjects are being able to control viremia. The other subject is, of course, a lot of the work that Rafi Ahmed, Marcus Halfeld, and many others have done is to show that HELP is absolutely essential to be able to restore CD8 cell function. So in HIV infection, you lose HELP. Of course, you lose T cell function. So here now you can imagine that you're putting back helper T cells which have been activated and are potentially fully competent, and now you're trying to test the hypothesis that by providing that non-cognate help or even cognate help, are you able now to promote restoration of T cell function? So that's essentially what you can see. In fact, is that if you look upon infusion at several weeks of infusion at the rescue of HIV-CD8 T cells in the 11 trial, you can see, in fact, an expansion of those cells that are HIV-specific and that make IL-2 and, make gamma interferon and TNF. Some of them can make also IL-2. So that treatment seems to have an impact on HIV function, and it's a correlated viral load because now when you do an integrated analysis and look at what differentiates the subjects that respond, the controllers from non-controllers, the controller in green and the non-controller in red, you can see that HIV T cells, TMs producing IL-2, and also the RA-RO counts at week 6 and at week 92 are two major features that correlate and control viremia. So not only protection of EM cells from infection and the capacity of T cells, to rescue their HIV-CD8 function, are two correlates of protection or control of viral load. So one of those subjects, patient 0160, recently entered into the SCOPE cohort that Steve and his colleagues at UCSF have been following, and we were able, in fact, to get cells from him 4 to 5 years after treatment. And that subject, in fact, was a subject, one of them that was among those that controlled viremia early on. And you can see, in fact, that there was an initial increased viremia, and then suddenly, the subject underwent decreased viremia, and now has viremia that's somewhere between 100 to 100,000 CD4 T cell copies of RNA, copies of RNA, and that subject, despite all the advice that Steve and his clinical colleagues gave to him, he doesn't want to go under treatment, despite the fact that CD4 T cells are decreased. But he is able to control viremia to levels which are below 1,000 copies of RNA compared to the initial rise in viral load that he underwent when he stopped treatment. So, in fact, that subject was among the one that had the highest level of pentamers, of mutations in his blood as compared to all the other subjects. All the other subjects were somewhere between 10,000 to 50,000. This one continuously, even up to 2,000 days after infusion, he's able now to maintain very high levels of pentamer in his blood. And of course, you cannot do a correlation of N of 1, but I mean, that subject, as compared to all the other ones that had to go back on treatment, has at least 10-fold or 20-fold higher copies of pentamers of the common mutation in his blood after 2,000 days, meaning, again, there is a population of cells that acts like a stem cell that continues to contribute viremia to viremia. And in fact, I mean, this, if you compare that subject, 060 to 059, which this one is a controller, you can see that this subject has high TSCM counts 6 weeks post infusion, and he has high L2 positive T cells in his CD8, so he's really peculiar as compared to all the other subjects that were used in this trial. So, and of course, if you look at the absolute numbers of this, the frequency of those cells, either as total cells or within the CD4 compartment, you can see that RARO TSCM, as compared to all the other subsets, is the one, again, that seems to persist the most in this particular subject. So we don't have a Berlin patient, we don't have a Cleveland patient or a San Francisco patient, but we have a subject that seems to control on his own viremia, and this is associated to the high number of TSCM that are still present in his blood. So if now we integrate all these different data, what we think is that, of course, pre-infusion, you have all these subsets that have DNA, viral DNA integrated into their T cells. When now you modify genetically the TSCM and eventually also the TM, and you infuse now those TSCM into the subjects, now you're able, to protect TM cells from the novel HIV infection. These cells, we know, are the ones that can support the highest level HIV application, and that allows you at the same time to reconstitute your CD4 counts and eventually to provide help to CD8 T cells, then eventually can control viremia. So that's a model that we will be testing, and I'll present to you this in the next subject. But before that, I want to thank, all my collaborators. It's really Jumana Zedan in my group, been with me since Montreal and Florida, and now joined me back again in Cleveland, who has been pioneering and developing all this work with the help of Glendak, Philippa, and Clarice. Slim and Ali are the one who did a lot of the bioinformatic work that I presented. A lot of the reservoir work that we measured was done by Nicolas. And of course, the trial was made by Delando and Garli, with, of course, Steve Dix, De Lazari, Balderas, Ronald Mitsuyatsu, and of course, Bob has always been very generous in his advice and his contribution. Of course, they are an MFAR, and the participants, they are an MFAR who funded the study, and the participants for their continuous, generous contribution. So now to the beginning of the future, which is this Trailblazer study that we'll be doing and I've provided you with some details in Cleveland, in San Francisco at the University of Cincinnati, where we'll be testing now the concept. So of course, when I present those data, everybody tells me, Rafick, how do you know that all of this is due to the CCR mutation, or it's just, some anecdote, where something happens in the subject which has nothing to do with the CCR5. So the only way to do this is to do a two-arm study, where now we have an arm that has the CCR5 mutation of subject that receive the CCR5 mutation, and a group that will not receive the CCR5 mutation. So first, what we hope to be able to address, instead of only look at total DNA or integrated DNA or tilde, we plan to look at the decrease in the HIV reservoir and focusing on replication competent virus, using both the RPD assay and also a mini replication competent virus assay developed by Diana Kulpa. And of course, the seminal question is really to address whether the CF modification is a critical factor in the TSM survival, CD4 reconstitution, and HIV reservoir decay when ART is interrupted. But we don't plan to do, at least at this stage, a twin interruption. The trial will include two arms. and we'll compare the effect of expanded oligo-CD4 T cells with or without ex vivo modification of CCR5G by zinc finger nuclease in HIV patients. We plan to include 30 participants in this study, and 20 in the modified arm and 10 in the control arm. Those participants will have to have plasma HIV RNA that is below 50 copies of RNA for at least 2 years. And then this 48 weeks, less than a year. And then CD4 T cell counts which are greater than 350 cells per cubic millimeter. And as I said, Benigno Rodriguez at Case is the PI of the clinical study, and of course Michael was instrumental in developing the protocol that led to the funding. The University of Cincinnati, Carl Schifferbaum, and Steve Dix are also sites where patients will be recruited. The participants will be randomized, as I mentioned. Initially, they'll be treated with CTX at the dose of 1 milligram before infusion. And we hope, I think we have one last step. The protocol has been already approved by the FDA. We have an IND, we have RBs for at least 2 sites, and we hope bearing on one last piece of paper that we need to get from the NIH to be able to enroll in next month. So this is scheduled CTX infusion of 5 to 4 billion cells. Again, the protocol is very, very intensive. We will be doing leukapheresis at baseline, at 1 year and at 2 years, and we'll be able to. We also hopefully will be able to consent subjects, to undergo biopsies, both lymph node and rectal, at 1 year and at 2 years, and measure integrated DNA not only in blood but also in tissues. And that will allow us to assess the first, what is the primary outcome, a primary endpoint, which is going to be of CCR5 modified T cells to decay or reservoir measured by the gamut of approaches that are being used now to measure fully replication competent virus, and also to assess the contribution of the adoptive transfer cells to now restoration of HIV-specific T cell function and global T cell homeostasis. So I'm going to show you a couple of slides that highlight the role of those TSCM in a completely different venue. So here, instead of looking at patients that were undergoing those clinical trials, we looked at patients that were either elite controllers or patients or subjects that were viremic controllers. So if you look at viremic controllers or elite controllers and look at viral load, you can see, in fact, that the elite controllers, as expected, have very low levels and several levels of viral load, while viremic controllers are subjects that are able to maintain high CD4 counts despite the fact that they have high viremia. And here is what you see. In fact, a lot of those subjects have CD4 counts which are almost as high as what you find in the controllers. So one tendency that you all have is to put everybody in the same bag, but you know that we are not controlling mice, so there must be differences. And we are able to unravel those differences. So now we look at globally in an unbiased way at gene expression. And when you look at those viremic controllers, and now you global gene array on them, you can see, in fact, that again they don't all fall in the same bag. Some of them segregate together with elite controllers, and some of them segregate together are all on their own. And so we call these VC stem for reasons which I'll show you now, while the other ones we call them VC exhausted. So the point I want to make is that from that slide is that viremic controllers fall into many different categories, and some of them have similar features to what elite controllers are. So now when we look at the frequency of stem cells of TSCMs in those subjects, we can see that those subjects measured by CyTOF have very high frequency of those TSCM, and that at even a CCR5 non-edited TSM can highly contribute to high CD4 counts, but also, unfortunately, contributes to high viral load, meaning that if you are seeding, those cells from the onset of infection, that will lead, to maintenance of high viral load, but also corollary at maintenance of high CD4 counts. And now if you look at the gene profile that is able to segregate, to correlate with high viral load, but also with high CD4 counts, this is really a stem cell signature that highlights by the frequent effect that you have here, the master gene of stemness, TCF7. And so you can see TCF7 is only expressed only in those substrates that have both high CD4 counts and high viral load. And I will not go through all the genes, but trust me, these are all genes that you know are features of stemness. And so the model that we have, in fact, is a model that even justifies even further, the intervention that I showed you earlier, because the model indicates that if you from the initial period of infection, the reservoir, the virus seeds those TSCM. Those TMs are long-lived. They are antiptotic. They don't die. They stay around, and they continue going to replenish the reservoir. But if you're able now to have an intervention that's going to be able to protect those stem cells from getting infected or for maintenance of infection, now we're able to choose a balance and probably result in the same parameters which I told you in the earlier phase of my presentation. So we went on and developed, we want to really understand what those stem cells are. And so we used many different approaches to be able to confirm they really behave like stem cells. So the first one is that those cells, clearly, when you compare them to all the other subsets or subset of the CD4-TM subset, you see that these are the cells that are unique in integrating all the different components of the Wnt-Notch response, going all the way from the ligands to the receptors, the frizzles, to the beta-catenin signaling, and of course to all the target genes of the Wnt-Notch pathway. So those subjects have really a unique Wnt-Notch signature, which is the hallmark of T-cell subcell. Those cells are also uncommitted, so they don't have, they don't produce any cytokines as measured by mesoscale. And also, if you look at now two transcription factors, which are related to commitment of memory T cells, you can see that those cells have hardly any Tibet, hardly any GATA3. We looked also at gamma T, FOXP3. They are truly uncommitted cells. So both at the level of signature, but also at the level of commitment, those cells are truly uncommitted, confirming that those cells are very early in the mature differentiation stage of CD4 T cells and are behaving like stem cells. So we looked at markers, set of markers, which are associated to stemness. And from our gene array data, we were able to show, in fact, that those RAR-int cells express very hard 4-1BB. 4-1BB is a molecule that's associated to stemness. In fact, Carl June and his colleagues have shown that when you have a 4-1BB tail, that leads to high persistence of CAR T cells in patients. And we have very similar data using our own CAR T cells in cancer. Another molecule that also associated to that people have been testing in CAR T cells are OX40, but you'll see that it behaves very differently for 4-1BB. So now we went on and tried to confirm now at the single cell level the stemness program. And what we did is to generate an in vitro system to trigger the differentiation of the stemness, those stem cells, by taking PBMCs, purifying CD4 T cells, stimulate them with CD28, and put them in culture with AL7915, and now sorting that part of the subset, which is RARO intermediate, and now with the help of Alex Shelek, develop single cell sequencing. And what we were able to show, in fact, if you look at the different clusters, which you can see in the previous slide here, now when we sequence all the different clusters, you can see that cluster 2 is quite unique. It has TGF-beta signaling, it has IL-2 stat response, it has a Wnt-Notch pathway, and it behaves very differently from all the other subsets. So now when you go and look at the single cell level and compare, that subset of the differentiated RARO cells to even sorted ex vivo RARO cells, you can see that you have the enrichment of stemness associated genes like LEF1, TCF7, and CD27, and CD1. I will not show you the whole list because it will bore you at the end of the day. I don't have as much time. And if now you look at the differentiated cells and compare with the 4-1BB, the OX40, or the double negative cells, and look at their single cell profile, now you can see again, those cells are very highly enriched in the stemness program, in survival programs, so anti-apoptotic, in TGF-beta signaling, and TGF-beta signaling is absolutely required also to trigger stem cells, and of course in genes involved in downstream of homeostatic signals like STAT5, which we know, IL-7, IL-15, both trigger through STAT5. So we have now a panel of 28 colors that allow us now to sort specifically those subset. And with the help of Bob, we'll be able to generate a panel that includes all these markers, and that will allow us now to monitor in our new clinical trial the fate of these cells over time, and whether enrichment in the frequency of those cells will be able to predict whether or not subject will have a decay in reservoir and a restoration of their immune function. So we're still trying to improve our capacity to be able to generate homogeneous population of cells, and we look at different cytokines. And one cytokine that I've been looking at very promising in terms of enriching in the stem cells is IL-1 beta, and that's something that we are now exploring. So at the end, what I'll be able, from the second part, I think in the first part I highlight the role of the stem cells in the capacity of these stem cells, in their capacity to contribute to control viremia and to decay in the reservoir by continuous reseeding of the mature subset by cells that cannot be infected anymore. And I think what I tried to do in the last few slides is really to focus on how we can improve on this. And we can improve on this by first be able to track those cells at the single cell level using high density flow, but also to be able to generate a product which is going to be very highly enriched in those stem cells, and hopefully in the next stage of once we are hopefully able to complete the first trial, we'll be able to do a second trial. So my last slide is really to say that there's not a single approach that's going to lead to HIV remission. You're going to need a combination potentially of all these different approaches. I know that Steve has now a trial that combines the adjuvant, the serovative vaccine, and the BNABs. And this is a crowd of people that I'm working with, and we're all trying towards an HIV cure. They're all hobbits, and I'm somewhere up there. And these are the hobbits that accept to work with me. So thank you.
So questions?
Rafick, I wonder if you could say a word regarding the stem cell modification and retransplant in terms of the potential for worldwide use, and assuming that that's probably not going to be very, very realistic, what we may learn from these studies, or ways that it could be modified or altered in such a way to make it generally applicable for worldwide use.
Well, to answer your question, this is why the Gates Foundation is funding me. And in fact, when I talk about stem cells, these are T-cell stem cells. So what we do is a very simple leukapheresis. We modify the cells and we infuse them back into patients. So we hopefully, by being able to enrich in T-cell stem cells, we'll be able to minimize our input. And yes, of course, not do bone marrow transplantation, just do a simple transfusion and infuse those cells back modified into patient. And I think we've been discussing now with people in Uganda about potentially doing a trial there once we've done this. So I think this approach, compared to the bone marrow stem cells, is log simpler. And I hope that to be able to implement it globally.
So Rafick, you had mentioned that you thought that IL-1 beta was important in maintaining memory stem cell-ness. Is this a direct effect of IL-1, or is it an effect of IL-1 mediated through an intermediary? I ask because we have found an intermediary in monocytes that responds to IL-1 by promoting a small population of CD4 T cells to expand?
So, I mean, it could be through an intermediate, but it's not monocytes because the culture system that you use to promote the differentiation of those cells, the culture system where initially we start with highly purified CD4 T cells and memory cells, yes.
The helper activity, I wasn't clear based on the stem cells. You said they didn't have either T-bet or and so on. How do they mediate the helper activity? I was a little unclear about how they're driving the CD8 effector function in this once you've created these.
Because, well, I think, I mean, like I mentioned, those cells don't have helper activity because none of the machinery that's endowed with Th1, Th2, Th17 is present in those cells. But, I mean, you assume that those cells, once you put them in a patient, are going to differentiate. And I showed you that those cells can become central memory, can become transition memory,
right.
And that it is now the progeny that's now more involved in the hyperactivity.
So one of the questions is you're looking, what happens since a lot of our HIV patients in cure are going to be in their 50s or even 60s, at least in a developed world. What happens to these cells and what happens to them functionally in aging? Because if you're going to be looking at them in terms of their functional activity, what happens in HIV and then in an aging patient as well across that in terms of how they'll be able to respond?
So I mean, so I cannot answer you what I don't know, but I can tell you is that, I mean, we up to the 5-year follow-up that we have on the 902 cohort, I mean, the average age of the subject between 47 and 52 years old. I don't know what they'll become 10 years from now. But, I mean, I would assume that because we reprogrammed, I mean, those cells when you ex vivo, that they'll be more long-lived. And I would assume also that those stem cells will be able to persist. Of course, I mean, you have subjects that have high levels of inflammation, like some elderly. That could lead to the demise of those cells. But these are things that we'll be able to figure out only when we do the clinical trials.
Rafick, those cells are infected by HIV, those stem cell RA.
So they can be infected. So we know that if you take them and they are not gene modified, they will be protected. I mean, they will be infected. They can be infected. If you modify them, if you self-modify them, they will become infected. In fact, I mean, the work I showed very quickly on the rhyme controllers tell you that the minute that cell gets infected, you're done, because it's very hard to eliminate them, and they constantly provide the fuel to all the other subsets all during your life. So the last thing you want to do is to seed those cells, and because they're infectable.
Okay, thank you.
Okay, Rafick, thank you so much.